Okay, so last lecture we were considering groups which had infinite number of elements. I mean, by that you mean, what I mean is order of the group is is not finite. The easy way to see that is if you consider a rotation, the angle takes a continuous variable, and so we will also use when there is some parameters. Okay, so even more, this thing is there were parameters, continuous parameters, that could be varied. So if you have a simple rotation in 2 dimensions also, you would write okay. So for every value of theta lying between 0 and 2 pi, you get a distinct element, and so this is a group which order is infinity. Okay. So what we are going to do is we are going to discuss what I will call finite groups, mainly because it is they are simple to handle, and a lot of ideas can be explicitly in fact in most math textbooks you will find that finite groups is discussed a lot more, while in physics books you will find that what I will call continuous groups are discussed a lot more, and this has to do with in the sense of applications or whatever you want to do in physics. This is what appears, but this is, I mean, it is not true that finite groups do not appear in physics. Of course it does, but somehow this is something which we learn first, and we learn this later. Okay. So what I am going to do now is, so let us go back to the definition of a group, and so let us say every group has to have an identity element, I will call it E, and after that just a bunch of elements G1, G2, so on and so forth, and say Gn minus 1. So now it is a nice set with n elements, so order of G is equal to n, the way I have written it, and quite clearly, because the composition rule can be written like a multiplication table. Okay. And by that what do I mean? What you do is you write something like this: E G1 G2 so on and so forth, similarly E G1 G2 so on and so forth, and out here you write E. Let us say we have to follow some convention. So the convention we will follow is that this acts on E dot E composed with E is E, E composed with G1 is G1, E composed with G2 is G2, similarly G1 composed with E is G1, this will be G1 composed with G1. Since there is no ambiguity, sometimes you just write G1 square. Of course G1 square should be one of these other elements because of the closure, but I do not know, because I am not specifying my group, I do not know what it is, so I am just sort of writing it out. But if I knew the group, I would write the corresponding element out here. So this is like the group composition law. Of course it is not enough to write some random set of entries out here. it has to satisfy the other axioms. Okay. So what we will do now is to do a very naive thing, is to ask, can we, for small values of n, can we construct some group which has that property. Okay. So we start with n equal to 2, that means the group has only 2 elements, let us call them E, and the another element should be G. So now we need to write out the multiplication law, which is very easy. So these entries are easy to write. So the question is, what can we write out here? Okay. So there are only 2 possibilities. Possibility 1 is that G square is equal to E, and possibility 2 is okay. It is not hard to see that this would require, I mean this would imply G equal to E. Okay. So then it becomes a group of order 1. Okay. Group of order 1 is boring, it has only one element, which is E, the identity element. So this is ruled out. So this is, so the table is complete. Okay. So now comes, what about n equal to 3? Okay. One can go ahead and write out a multiplication table which would have 9 entries, and some of them again would be fixed very easily, but then there would be other entries. But we can ask, we can pick any one of these elements. So let me choose G1 and ask, what is G1 composed with itself? This is what I call G1 square out here. So what are the possibilities for G1 square? G1 square, if G1 square was E, what will happen? You will go back to the earlier group, it closed, it is over, there is no way of generating the other person, closure tells you that is over. So G1 square cannot be G for the same reason as this, but G1 square cannot be E because we want a group which has 3 elements, not 2. I hope you understand that if I put G1 square equal to E, it is not like I get, then what is G2? Multiplying these things, you will see you will run into contradictions. So what is the possibility? So G1 square, so the only possibility okay. So you can see for n equal to 3, I can just go ahead and write, instead of writing something like this, I just have one generator G, the other one I will just denote it by G square instead of calling it something else. And next step would be, what would, so we need to ask, so we have generated all the elements, so now all we need to do is, what is G times G square? What should that be? That should be E. Okay. So check for yourself. That is the only possibility. It is not too hard, because if G cube was some new element, then you are extending the group and you are getting something this that you do not want. G cubed equal to G again is similar contradictions, so on and so forth. So this is the only possibility. So subject to the relation, so G square G cubed equal to E. Okay. So this is completely abstract, we have not even decided what this set is or anything, we just wrote 2 elements and we wrote out, I mean the axioms or the definition of a group, and we find that we get there is only one possibility in these 2 cases. Okay. but of course as n keeps increasing you will see that there is more and more chance for you to construct new groups or whatever, but the first thing to do is to look at these two groups and see if you have ever seen anything like this. So let us start with n equal to 2. Have you seen this particular group in some form or the other? Binary numbers, okay. So that means this is a group which is if you take the set to be 0 1 or okay 0 1 with the operation plus mod 2. I do not know how the notation is. So 1 plus 1 would be 0, okay. So this is one realization, but in this course have we seen it before? Have you seen anything like this? Huh? Isoscalar. Isoscaling. What is that?
Triangle that three sides are equal. Then I can rotate.
No, I am talking about an example. I claim that we have in our previous lectures, last 5 lectures, we have seen an example of it. Parity, okay. So, but parity we realized it as a matrix, it was very different, but okay. So you take your set to be the identity 3 by 3 matrix and this matrix P, again this satisfies the same, okay. So let us just do one more thing, let us define this thing to be R of theta, okay. Let's take R of 0, take G to be R of 0 and R of pi, okay. So this would be, so pi of 0, R of 0 is identity matrix, R of pi is minus 1, again that is also a realization of this group. So what you see is that here this is a 2 by 2 matrix, here it is like just one element, one dimensional thing, but the operation. So in these two cases the operation is just group multiplication, but here it is modulo 2 addition, but they are all from the abstract group that we have written, okay. They are all realizations of that, okay. So what the statement, the mathematical statement is, all are examples of a group of order 2. I do not need to say which group because as we saw it is unique, okay. So these instead of calling examples we will call them or realizations, these are all English words, but the precise statement is that they are all representations of this group, okay. So the precise statement is I still have to define for you what a representation is, okay, but it just means this sort of a thing. Precise statement is that the 3 examples are representations of the group, okay. So what you should have in mind is when we talk of a representation usually is if you give me a group element, it is mapped to some matrix, okay. So for all okay, so every group element you will give me a n by n matrix, and so such that the product the composition law such, and it should satisfy closure etc. G1 dot G2 will get mapped to so n stand for matrix out here. So, for G1 we get an n by n matrix, for G2 we get an n by n matrix, and the matrix is such that it respects the composition rule. So, on this side it is the composition rule in the group, here it is the usual matrix multiplication. Okay.
Whenever we say representation, will it always be square matrix and matrix multiplication as a composition?
Yes. So, the even more precise statement is that it acts as a linear operator on a vector space. So, if you take a linear operator that it is realized as n would be the dimension of the vector space. Okay. So, we have already seen, for instance, when we took the SO3 rotation group, the vector representation. So, you can think of the SO3 as some abstract group with some multiplication rules, and we wrote 3 by 3 matrix realization. We also saw a 5 by 5 realization, because when we took a symmetric tensor, traceless tensor, we saw that behaved. So, if you worked out the thing, that is like a 5 by 5 representation, and in your quantum mechanics course, if some of you have done quantum mechanics, you would have learnt the spin j representation is 2j plus 1 dimensional. So, what that means is that for the SO3 group, every element will be realized as a 2j plus 1 times 2j plus 1. So, what I call n here would be a 2j plus 1, n would be equal to 2j plus 1. Okay. So, but let us get back to what we wanted to do, which is to go ahead and so you can see out here again this thing I can think of n equal to 3 as rotations by 2 pi by 3. So, pi here I can rewrite actually as 2 pi over 2. Okay. So, I can realize this property, something which cubes to 1 is like a rotation by 120 degrees. So, I have 120, 240, so on and so forth. Okay. So, let us just define a group. For any n I can do this, for any n I can. So, we have actually, by looking at these two examples, we will get for all n we can write a group like this, and I will, so let us call this group Zn, okay, and this is true for all. Okay. So, there is no restriction on n. So, for any given n I can write such a group. Okay. So, you can, like I said, again realize you can look for a representation in terms of just 2 by 2 matrices in terms of rotations. You can also think of them as mod n addition, there is no problem with that. Okay. But the question is, are these, I mean these is this the only group? It is very boring, and look at these groups, they are abelian, because it does not matter how you. So, let us say that if you take any G1 dot G2 is equal to G2 dot G1, how do you see that? Any G1 can be written as G power some m1, and any G2 can be written as G power m2. So, implies that G1 dot G2 equal to G power . So, this is a group which is abelian. Okay. So, now the question is, can we construct more groups, and the answer is yes. So, the first example would be to look at Cartesian. So, you take any two groups, say G1, let us call it G and H. You know what the Cartesian product of the sets are. So, I just need to tell you what is the composition rule. So, let us say that the set of this has elements, which I will write as E of the group G, no other way around. Okay. So, this would be in terms of set theoretic language would be a generic element which would look like G1, G1 and some H1 for some, right. This is what would be a typical element of this space. So, we just need to ask how do we multiply two elements, and it is very obvious to convert it into a group. I need to just tell you how to multiply. How would you do that? Any ideas? Because we know how to multiply G1 and G2, we also know how to multiply H1 and H2, you just do it that way. So, this is the natural one. Okay, where this dot here is the composition in this group, and the second dot is the composition in that, and so this is just definition. You can see that the identity of this product group is EG, EH is the identity. Okay, so this forms a group. So, you can again you can see starting from this we can construct a few more. Okay, so an example would be and you can see order of this group will be order of G times order of H. So, this would be order 4 group. So, we already have one here which is Z4, but this would be also an order 4 group. Okay, so, let us say the elements of this are E, I will not put the subscript here, but I will use a different symbol for this, EG out here, I will call this EH. So, this set will have the following elements E comma E, G comma E, E comma H, G comma E. Okay. So, I have an exercise for you which is the following, which is to take consider an element a group with with 4 elements. We have 2 examples. The question is, are there any more? The answer is there are no more. Okay. So, there exists. So, claim show that these 2 examples, that is of groups of order, actually just call it these 2 groups of order 4 are the only such groups. So, I mean one horrible way to do it is to go ahead, write out the composition table and convince yourself that there cannot be any more. Okay. There is another nice I mean theorem or whatever, when n is prime, okay, when n is prime there is only the group is necessarily ZP Zn rather, there is no other example. And the way to do it, can anybody think of how to prove it? So, prime, what does it mean? If something is prime, it means it cannot be factorized. Okay. So, let's so you just arbitrarily take the so you write out a group with n elements where n is prime, pick an element which is not identity and then start taking powers of it. Okay. You keep on going and at some point it has to terminate, but the only point it can terminate without any contradiction is when it hits n. Okay. So, for prime numbers actually you are done. So now you can see that with my claim in this thing I have actually completed all groups of order less than or equal to 5. I have completed everything. 2 is prime, 3 is prime, 4 is not prime, it is composite. So there were 2 possibilities, which I mean if you believe my claim, and 5 is prime. So we are done, and so we can see that until order 5 all groups are only abelian, there are no non-abelian groups. Okay. So let us see one more example which comes in physics quite a bit, which is looking at symmetries of polygons, regular polygons. Okay. So by that I mean take something like this is a triangle, equilateral triangle, take a square, then the next one would be a pentagon, hexagon, so on and so forth. Okay. So ask for all the symmetries of this. So you look at, so one symmetry is you pick the center of this object and rotate by, we will not look at translations, so we will preserve something. So you take a rotation by 2 pi by 3 here, 2 pi by 4, etc. Okay. So the symmetries are of a regular n-gon, that is a polygon with n sides, it is a rotation by 2 pi over n, which is like a Zn. Okay. And there is also, I can pick something like this, I can reflect about, this goes here, this goes here, but it is a reflection, so it is a Z2, but there is nothing special about this. I could have chosen this, I could have chosen this also. Okay. Similar things you could see out here, you could take for instance here, take something like this. Okay. So you also have reflections, several reflections. So let us pick this particular case and let us call this reflection R1, 1, 2 and 3, R1, R2 and we will call this R3. They are all reflections. They all satisfy a nice condition, which is R1 square equal to identity, I will write it equal to 1, but I mean identity. Okay, these are operations, but now the question is what about R1 R2, is it equal to R2 R1? Okay, so go back home and convince yourself that is not true. Okay. In fact, you can show that R1 R2 composed, R1 composed with R2 is equivalent to a rotation. Okay, let us call this rotation, we will call it x. So this would be something which would satisfy x power n equal to, let us put identity as E. Okay, x power n equal to E. You can show that R1 R2 cubed equal to, so 2 pi by 3 here, right, because we are looking at for, oh I was doing an n-gon. So sometimes I get very ambitious, so let us make let us leave it as triangle, we will write the general answer later. Okay, sorry. So what we will have is R1 R2 cubed equal to identity. So it is one of these rotations by, okay. So in other words, this guy can be generated by all these things, and you can even convince yourself that I can generate, given R1 and R2 I can generate R3. So homework is go back and play with this triangle example, and you will see that everything can be generated starting by any taking 2 of these guys. In fact, it generalizes to the n-gon, where there will be the analog of this r1 r2 r3 up to rn, all of them square to this thing. Okay. So this group, and its important thing is r1 r2 is not equal to r2 r1. Okay, it is a non-abelian group. Okay, and let me write out the group for you. So the group, this group, symmetry of a triangle. Okay, so we will just call it D6. We will see what the 6 means. Generated by 2 elements R1 and R2 which have the following properties. Okay, and it's not it's not so hard to see that R2 R1 is equal to okay. So I generate even this other thing, I leave it as an exercise for you to determine what R3 is. Okay, so this group actually has exactly 3 elements. You can also rewrite it in a slightly different form. I just pick R1 and I call R1 R2, let us call it X, with the following. I still need to say okay. With this way of writing it, you will, it is not hard to see that I can write out all the elements. It will be identity x square. Okay, I can't write x cubed, but I can write r x square. All the others, anything else I write will get simplified. So I have dropped this r, I have not written 1 out here, maybe I should. Okay, so we have a nice group which has 6 elements, that is why it is called 6. D stands for the dihedral group. Okay. So more generally, I will define D2n it is exactly like this, except I put if I put n equal to 3 I get D6. Okay. You can convince yourself that the number of elements is exactly 2n. These are non-abelian groups. Okay. So you can see the non-commutativity straight away built in here. Okay. So actually there is a nice if you see here that in this first way of writing this group, it was written in terms of elements which all square to identity, they are like reflections, they are like Z2s, but their composition behaves has some properties like this. Okay. So this also has a name, this is called, so such groups are called Coxeter groups. Okay, so where I am not writing, I mean it is quite different from what we did earlier. We tried to write out the all the elements and work out the multiplication table. Here we are writing in terms of some generators with some relations. Okay. So you can see that this is a natural generalization, even this is written in this way, in that presentation it is just saying that it's given by one generator with one relation, but here it is somewhat different in the sense that all the generators are always Z2s, okay. They are also called Coxeter groups. So this is actually in fact the smallest non-abelian group, okay. We will see another whole family of non-abelian groups. Again one can write another order 6 group which would be abelian, which is Z2 cross Z3. So here is a case where you can use the non-abelian nature to prove these two groups cannot be equal to each other, there is nothing to compute. Z2 cross Z3 is by definition it is abelian, okay. So here is another nice idea which I already discussed, the idea of a subgroup. Subgroup is that let H be a subgroup of G. So H and G, by the way, whenever you mention a group and I do not I will not keep writing originally my definition of a group at G with some operation, it is sort of annoyance to keep writing the operation. So you just usually one just refers to the group G, and until it is necessary you do not specify the operation, okay, or in context you know what one means, okay. So here what I mean is that G with some dot is a group and H with the same dot is also a group, okay, but it is also a subset, okay. So here is a nice an important theorem which says that order of H divides order of G, necessarily so, okay. So you can see now if order of G is prime, it cannot have any subgroup, it can have a subgroup, one trivial subgroup which is element with one, okay, one element E or itself, okay. So these are the two I mean, so I am not I mean in principle it could be equal to that, any group is its own subgroup, obviously order of G divides order of G, okay. So you can see that so this implies that when order of G is prime, then it has no non-trivial subgroups. Okay. So now the question is how are we going to use this fact and prove this, and this leads to a beautiful construction, and so this needs me to introduce a simple mathematical idea. What we will do is we will if H is a subgroup of G, suppose I was able to partition G into given H, partition G into equal sized parts, yeah, okay. Then it follows for so every element of H I will give you one part with a label going with that, so that will lead to a partition of the sets, and if I can show that each partition has the same number of elements, then I am done, okay. We will do that, okay. So we need the idea of something called an equivalence relation. It's a beautiful idea, okay. So let G be a set. This is one of the cases where being formal, writing out the thing is better than anything else, okay, with elements of course. G1, G2 etc., okay. Then we can define one defines a relation set by saying that G1 is related to G2 and so on and so forth. So, there might be two elements which may not be related. Okay. So, it sort of it says that G1 is related to G2, maybe G1 is also related to G3, so on and so forth. Okay. If every element is related to everything else, it is not very interesting. So, there will be, so we have to, the relation is specified by giving all the all possible relationships in this group. Okay. So, so an example would be, this does not require this to be a group or anything. Okay. So, for instance, if you take a population of a country and say that we define two people are related to each other by some blood relation or whatever. If you do that thing, what will happen is that you will find that that is like putting a relation on the set. Okay. So, there can be two people who are not related to each other. Is that clear? Okay. So, we will so the if a relation satisfies certain conditions, we will call it an equivalence relation. Okay. So, the first one is so these are, a relation is said to be reflexive if any element, if any element is related to itself. Okay. Second one is symmetric if G1 is related to G2, it implies, see for instance, if you said the relationship is say a brother, okay, somebody can be the brother of somebody, but the converse need not be true. Why is that? There could be sister, right. So, it is not a symmetric relationship. The last one is transitive with T or whatever. If G1 is related to G2 and G2 is related to G3, then okay. If all this is true, then I claim that it is the same as partitioning this set into bunches, each basically people who are related to each other, the group elements who are related to each other. It is like the family. Okay. Is this clear? You seem very unhappy with this. Yes, yes. G1. So, you pick. So, what you the partition is as follows. Let us do it. Pick one element from the set. Let us call first element G1. Then scan through the whole thing and pick all the elements which are related to G1. Then you are done. Now, you look at what remains. Okay, there will be some elements which are not related. Pick the next element. Okay. Again, you look for all the elements which are related to it. Again, you form the second part, third part, so on and so forth. It gives you a partition, and you need to think about it that you need all these properties. Otherwise, you will run into problems. You will not get a partition. So, what an equivalence relation does for you is to take a set and partition it. Okay. So, now what I will show is precisely that. I will show that given H, I will define an equivalence relation, so that you will see what that is. So, let us. So, I need to define an equivalence relation. Okay. So, we go back to our original problem. H is a set and G is also another set. So, let us define. So, okay. So, let us denote all elements of H. Of course, identity must be in both. Okay. So, I have to say that G1 if there exists some H belonging to H such that okay. So, reflexive is trivial, okay. There is nothing to choose, H you have to choose E, okay. So, that is done. Symmetric again it is not so hard, I can just this implies G2 equal to G1 dot H inverse, but that is guaranteed because why is that guaranteed? Yeah, inverse exists, H is a group. Transitivity again is not so hard, okay, it is trivial. So, it satisfies the equivalence relation. So, now let us ask what is the partition we would do, okay. So, the claim is G can be written as, so you pick an element of E and ask for all the elements related to it by the action of H from this side, okay. So, what will happen that because the first element we have chosen is E, it will give us all the elements of H. So, the first partition is H itself, the group H, okay. Next one you pick another element, let us say it is G1. So, let me write this as E dot H to remind you where it came from. The next element will be G1 dot H, so on and so forth until you are done. Now, you can see each of these elements, each of this partition has how many elements? Same as H, same as order of H. So, now there are certain numbers. So, the order of G is the sum of these things, each of these elements. So, this implies order of G is equal to order of H times number of partitions. Okay. If the number of partitions were 1, then G and H are the same, that is we said it is a non trivial subgroup, okay. So, that is gone. So, it has to be at least 2, okay. So, this proves this theorem, okay. So, the partition here can be understood, I can rewrite, I will define something, I will call the partitions G mod H, this is just a definition, okay. The notation here is for E is a symbol for this partition, I group all of them and think of them as one element, okay. Similarly, G1 is this element, but actually any element, it does not matter which element I choose, I will choose just one element in that partition and plug it in there, okay, so on and so forth, and I will write this thing as follows, okay. This has a name, it is called a coset, it is just a set, it is a set of partitions and each partition should be given a label, I label it by any one of its elements. In particular for this I have said it is E, but I could have put, in fact I could have put any element of H into it, okay. Now, again coming to this whole setup, in this equivalence relation I put H on this side, on the right side, I could have put it on the left side, it will give me a different partition, okay. So, they have names, we will call this a right coset. In general it is just a set, it is a set of partitions of given a subgroup, okay. The other one is called a left coset. So, I will stop here and ask the following question, which I would ask you to think about, can a coset be a group, is there a natural action? We know that there is coming from some bigger group where there is a group action. So, by that what do I mean? If you give me 2 elements, can I define does it take me from one partition to another, is it possible, what are the conditions under which it can happen, okay. Like I said, this may not happen, but there are some conditions under which a coset is also a group. Okay. So, I will leave you with this puzzle, you should go back and play with it again, because this is a non trivial test of what the axioms are, of your understanding of these axioms. Okay. So, you have to ask what will happen, and there will be a nice abstraction or whatever which you should see. Okay. And so, I recommend that you play with this and see for yourself how that works out. Okay. I will stop here, but next time we will look at permutation groups. These in some sense generate all groups can be, all finite groups will be subgroups of some permutation group. Okay. So, in some sense that is like the permutation group is the mother of all finite groups, in some sense. It is not a single group, it is a family of groups, but we will see why that is plays a very important role. And so, lots of things about finite groups can be understood by embedding it into some permutation group. Okay. So, I will stop here.